Okay, in this video we're going to put a bunch of stuff that we've been talking about together, and we're going to use it to figure out how many moles of some substances we have, and then use that to figure out how many particles and work through some of that kind of stuff. So remember, the molecular mass is the mass of 1 mole of a substance, and we can use this to figure out how many moles we have. And since we know how many particles there are in a mole, we can also go all the way to figuring out how many particles we have. Let's start with something simple here. How many moles of copper are there in a penny? So I looked up online what the mass of a penny is. It's 2.5 grams. How many moles of copper are there in a penny? The molecular mass for copper, I gotta look this up, hold on a second, is 63.55 grams per mole. So that's the mass for 1 mole. The mass that we have is 2.5 grams. So we can figure out the moles by figuring out our mass divided by the mass for 1 mole. 2.5 grams divided by 63.55 grams per mole. So we don't have a full mole here, we only have 0.0393 moles of copper. We can do this using the factor reduction method as well. If we view this mass of copper as in grams, then if we want to convert that to moles, what we need to know, so we're going to divide out the grams and leave ourselves with moles, is in 1 mole, how much mass do I have? And that works out to be 63.55 grams, right? That's the amount of grams in 1 mole. So 2.5 grams, and since the 63.55 is on the bottom, we divide, and we're going to get back to 0.0393 moles, canceling the grams. So either way you look at this, this is a formula you can always use, right? The mass of something divided by the mass per unit will tell you the number of units. Or if you want to view it as a conversion, where we're getting rid of grams and adding moles, and we have 1 mole is equal to 63.55, then that works out to division. Either way you think about it, you end up with 0.0393 moles. How many actual copper atoms are there? Well, we'll remember that our moles was equal to our number of particles divided by the number of Avogadro's number, the number of particles in a mole. So here, 0.0393 moles is equal to the number of particles divided by 6.02 times 10 to the 23 particles per mole. And so multiplying this out, I got 2.37 times 10 to the 22 particles. So that would be how many actual carbon atoms there are in a penny. Again, quickly, I can do this with the factor reduction method. If I imagine that I'm converting from moles to particles, I want to cancel out my moles, I want to introduce particles. I know that in every 1 mole there are 6.02 times 10 to the 23 particles. That's a 3. So it's the same multiplication, leaving me with 2.37 times 10 to the 22 particles, or in this case 2.37 times 10 to the 22 copper atoms. We can work this the other way around as well. What is the mass of 1.45 moles of carbon dioxide gas? Careful here. Carbon dioxide gas is CO2, so if I want the molar mass of CO2, I've got to add the molar mass of carbon plus 2 times the molar mass of oxygen which works out to be 12 plus 2 times 16. Again, I know I'm rounding here, but makes it easier. 44 grams per mole. So that tells me the mass for 1 mole of carbon dioxide. So moles is equal to mass over molar mass. That's my equation. If I want the actual mass here, I have 1.5 moles mass, and then there's 44 grams in each mole. So if I multiply that out, 1.5 times 44, I will realize that I have 66 grams of carbon dioxide in 1.5 moles. If I want to use my factor reduction method, or if I want to use this as a conversion, think of this as a conversion. 1.5 moles. I want to get rid of my moles and move over to grams. For every 1 mole, I know that I have 44 grams. So multiplying that out, I get 66 grams. Either way. And you can put subscripts on all of these things so that you can keep everything straight. So, in the end, regardless of which way you think about it, 1.5 moles of carbon dioxide has a mass of 66 grams. Or we can work all the way from a set number of molecules all the way up to mass. So this is going to be my last example. I'm going to do this one first with the factor reduction method because I keep doing that second, and then I'll do it with the formulas. So I have 1.5 times 10 to the 26 particles, or molecules if you will. The first thing I want to do is convert this to moles, because once I have moles then I know the mass of a mole, so I can work from there. Particles, moles, so I want to convert there. So 1 mole is equal to 6.02 times 10 to the 23 particles. Particles cancel, I do the division. And I see that I have 249 moles. Or if you prefer the formula, remember that the number of moles is equal to the number of particles divided by Avogadro's number. So you can get to 249 moles that way. It's important to go to moles because we want to get to mass eventually. Sorry, that mass. So now we know the molecular mass, or the amount of mass in 1 mole of these things. Calcium nitrate is Ca. Careful here, it'll be NO3, but calcium was a 2, so when I crossed it over, it's a 2. So I need the molar mass of calcium plus 2 times the molar mass of nitrogen plus 3 times the molar mass of oxygen. All in. Calcium is going to be 40 plus 2 times 14 plus 3 times 16. Doing this all on the calculator here. I got 164 grams per mole. So I got 249 moles. Now using my factor reduction method, I can convert that to mass. So 1 mole has a mass of 164 grams. Canceling my moles, I see that I'm multiplying here. Times 49. I got 40,836 grams, or if you want, 40.836 kilograms. Or, if I want to use the formula, N equals the mass of my substance divided by the mass per 1 mole, or the molar mass. Here I had 249 elements. My mass, each one weighed 164, and so my mass works out to be 40,836 grams. Either way you like to think about it, it doesn't make any difference. So there you can go all the way from particles to mole, particles to mass, or mass all the way to the number of particles. Remember, in chemistry, and this is always going to be the case, we're always going to be going to moles and out of moles. So we could be coming from mass, or we could be coming a number of particles to moles, and then we could be going out to mass, or we could be coming out to number of particles. But sometimes they call it the mole hub, because since moles represent their number of, or a usable number for the number of actual things we have, number of actual atoms we have, particles we have, it's a useful thing to convert in and out of when you're trying to work in chemistry between mass and number of particles, or a whole bunch of other stuff, concentration, pressure, volume, all this stuff is going to come later in the course. And we're going to be constantly doing this, converting to moles, convert out of moles.